Welcome for this session. We'll maybe going to start. We are just on time. We are going to start with this sixth session of a webinar of IIFC. Kent, I'm very pleased to welcome you for this webinar. You will introduce a new topic about full FRP system, and with an original presentation on the problem of compression and lateral buckling, I think. And then Kent Harries is an associate professor in Pittsburgh University, if I'm correct. And so I think now it's up to you to introduce maybe your presentation and yourself a little bit more if you want. And you can go, I think, with this. We are not going to wait anymore. So, Kent?
Okay, thank you. I appreciate it, Emmanuel. It's a great opportunity to get the word out about some other activities that are going on with IIFC. And the focus of today's presentation is a little bit different than what we've been looking at in the past. We have a lot of focus on concrete repair and whatnot. And the use of FRP in the concrete environment. What we're going to talk about today is the use of pultruded GFRP sections, and I'm going to specifically focus on tube sections in terms of all GFRP type structures. And so these are generally fairly specialized structures, cooling towers and what have you. I need to introduce my co-authors. Most of this presentation is based on the PhD work of Daniel Cardoso, who received his PhD from the Federal University of Rio de Janeiro last year, and he was co-advised by myself and Dr. Batista, who is a professor at UFRJ in Rio as well. And so certainly Daniel did most of the work. Excuse me. All right, I just need to. Okay, so. The impetus behind this discussion really is the development of standards and guidelines. Presently, there are really no international codes. There are no code documents specifically dealing with the use of pultruded sections. There are some documents that are out there. There's the AIFC Design Manual for Plastic Structures, and there's the Eurocomp Design Handbook. These aren't completely in codes and standards type format. And the real focus of today's talk is the building of this AIFC design standard, the so-called FCAP standard, which is still in development. It's being validated constantly and hopefully will be available within the next year or two. And so what we're really looking at is one particular chapter, one particular application where we have elements under concentric compression. And we'll talk a little bit at the end of the presentation about extending this. And so we're talking about columns, or we're talking about members in trusses, very common uses for these pultruded sections. Excuse me. And these approaches, we take a limit states type approach, and typically we're going to look at the limit state of a compression member as being the least capacity associated with the calculation of global buckling, local buckling, and then the squash loads if we've got very, very short members. And this works very well when we talk about isotropic materials like steel, but it ignores the issues associated with interaction between failure modes. In particular, the interaction between global and local buckling, which becomes more significant when we talk about orthotropic materials such as FRPs. We also need to talk about imperfections when we deal with steel, designing steel columns, for instance, the empirical equations that we use, the limits for slenderness that we use, include these imperfections based on standard tolerances that we're all comfortable with. In the pultruded FRP world, we don't have yet very good handle on what all of these tolerances are. They vary a little bit more internationally than we may be comfortable with, and so we do need to be able to consider these imperfections. And so our approach is simply using the old-fashioned column strength curves And wouldn't this be a more rational approach to developing the compressive capacity of FRP columns? And when I'm talking about FRP, I should clarify, we're talking about glass fiber reinforced pultruded members only. Excuse me. So we're really looking at a couple of issues here. We're looking at squash loads are very easy to calculate, and they're really not that much different. So we're talking about global buckling, which is essentially calculated as the Euler buckling load, and local buckling. And presently, in the available standards, the available guidelines, we associate local buckling with simply supported conditions at the plate intersections. And so a web and a flange are supported at a pin, which of course is not kinematically correct, although it results in relatively straightforward calculations. And so if we take a look at these, we have some issues associated with both the global buckling and the local buckling. In terms of the global buckling, one issue is that when we're dealing with GFRP sections, pultruded sections, we have a very, very low shear moduli. And in addition, the transverse shear effects are very different, or can become very significant when we're talking about short sections and even intermediate length columns. And these, can be very difficult to obtain. The standard tests are fairly straightforward. We can go to ASTM, we can go to ISO and come up with standard tests, but the dimensions that we need cannot actually be obtained from most commonly produced pultruded shapes. Very large shapes we can obtain the specimens, but not for some of these smaller 100 millimeter shapes that we tend to be using. And so we have some problems up in here calculating global buckling behavior. When it comes to local buckling, and I'm going to discuss this at the end of the presentation primarily, this assumption of simply supported conditions is simply not kinematically correct and doesn't represent the real mechanical behavior. And as we're going to see, it results in very conservative estimates of local buckling capacity. And I'm going to come back to this second point at the end of the presentation. So if we take a look at the compressive capacity of a pultruded section, we need to consider the second order effects of both the member itself, so the global buckling, and we've got an image here of a GFRP tube under concentric compression, and if you take a look, you can see that it definitely is buckling, in a global sense. It's bowing out sort of away from the camera in this particular case. And so we've got second order effects that are global, affecting the member, but we also have second order effects affecting the plate in compression. And if you look very carefully where these yellow arrows are showing, you can see the shadows of the rippling, the buckling along that compressive face. And so we have a local second order effect as well. And without doing any experiments, we can go into theory, go into fundamental mechanics, and we can derive a normalized strength relationship that accounts for the second order effects in terms of both member and plate or wall effects. And this is our equation here. Fundamental mechanics, there's no empirical factors at all. However, there's a lot of input into this equation that we're going to need some empirical data. We're going to need some experimental data. Alpha is the column imperfection factor addressing the out of straightness of the element itself. And rho then is a factor that talks about a reduction associated with the wall itself, the slenderness of the wall plate. And this itself is a function of the slenderness of that plate and the imperfections of that plate. And so we've got a lot of factors that we need to address. And that's what we're going to look at here in the first part of this presentation, an experimental program that aimed at nailing down these values and categorizing GFRP sections in compression. Critically, one of the reasons that we need to look at this interaction is if we just take a look at a normalized capacity curve, so essentially that equation that I just showed, versus column slenderness, so this is the overall slenderness, we can get our fairly traditional buckling curves, and the black dotted line is our perfect column, our Euler column that we're all familiar with, and then our curved lines are the reductions associated with whether we have very stocky wall sections, very stocky plates, or very slender plates. And what's interesting is because of this interaction, we actually see a greater reduction associated with intermediate plates, plates that fall between compact and slender, and we have a greater reduction in this region here. Certainly as we go out to very, very long columns, Euler buckling takes over and plate effects are minimal, as we will also see experimentally. And so what we did, I'm going to take a second to discuss this plot, because we're going to see a couple versions of this as we go on today. This is simply a mapping of GFRP sections. So across the horizontal axis, we have the column slenderness. This is the overall member, and so we have very, very short columns here on the left, going to extremely long columns to the right. And vertically, we have then the plate slenderness, the walls that make up these elements. And in protruded GFRP sections, for the most part, the thickness of the plate elements is uniform throughout the section. So if we have an I shape, the flange and the web tend to have the same thickness, and certainly a box shape always will have the same thickness going around on all walls. And so we have very, very compact, thick plates. They're very rare in protruded sections, to very, very slender plates up here top. And the definitions of the slenderness there in terms of the plate and the columns are given on the left. And so what we have here is a mapping of a lot of the current work that's out there. The little I shapes are, of course, compression tests of columns, of I-shaped columns. And we see that I-shapes tend to have relatively slender plates, in some cases very slender plates as we're going up here to the top, and we don't even really get into this intermediate range. And so I-shapes in particular are going to be significantly have second order effects associated with the plates and typically the flanges. Tests, of course, have been conducted over a wide range of column heights. For box shapes, we tend to have slightly stockier plates, slightly stockier walls, and we're in this intermediate range. But we still see a large number of gaps. And so I'm going to talk about a study today that hopefully fills in these gaps, or helps to fill in these gaps. So these red data points are the data points corresponding to the study I'm going to be talking about, where we really tried to fill in these intermediate and even getting down into some compact wall sections. And with these intermediate length elements, which are actually very common when we're using protruded GFRP sections, simply because we tend to be building, as I said, cooling towers and what have you, where we don't have particularly long members in compression. We're not studying too far out here with the long columns. We know that they're controlled by Euler buckling, and there's not much interaction with the plate slenderness. And so this is the area that we're working on. So what I want to do is to take you through briefly the experimental program. We studied the effects of wall slenderness, and what I want to do is highlight some of the issues that we come up with when we're dealing with protruded FRP, and I appreciate that protruded FRP may not be as well known to some of the people joining us today. So we looked at 5 different shapes, box shapes from 25 millimeters up to 100 millimeters. Boxes, very typical protruded shapes, and wall thicknesses of 3 millimeters and 6 millimeters. And immediately when we're talking about protruded shapes, the wall thicknesses don't tell us the entire story. We need to recognize also the architecture of these walls. And this is the actual architecture of the walls that we're using in this study. The 3 millimeter walls have a single roving of glass, essentially at their mid-level, and a fiber volume ratio of somewhere around 40% as a result. The thicker 6.4 millimeter walls actually have 3 rovings, one in the middle and then to either side of that. Slightly larger fiber volume ratios, up around 50%. But the geometry of this, or the architecture of these walls, is very, very important. Because what we're interested in when we're talking about compressive behavior is not only axial or extensional modulus, E times A, but also the flexural modulus, E times I. And while E times A is proportional. We can talk about simply the fiber volume ratio for either of these architectures. It should be fairly clear that the modulus EI, or the moment of inertia I of this wall shape, of the 6 millimeter wall shape, is going to be significantly different than that of the 3 millimeter wall shape. And more importantly, the relationship between these two moduli is very important when we talk about this buckling interaction. And very clearly, while EA may be very similar in these two, EI is very, very different. And so that relationship is different. And that is going to be critical and is going to be a function of the protrusion itself in the architecture. We looked at column slenderness in order to address the effects of column imperfections. This is just one case of columns that we looked at. This is the 50 millimeter box, and we tested very short 250 millimeter sections all the way up to 1700, very, very slender 1700 millimeter columns. Generally, the product that we were working with, which was made by a commercial protruder, was very, very good. The dimensions were well within what we would expect of typical tolerances, certainly within 10% of the nominal values. The one exception, and I pull this out here because it's something that we have to be aware of in terms of working with protruded shapes, was that the very small shape, the 25 by 3.2, we see that the wall thicknesses actually varied by about 15% going around this shape. And that could certainly affect our interaction, or buckling interaction, if the wall plate buckling was a factor. And so we do have to recognize that the imperfections can be significant in some cases and need to be accounted for. There's a lot of data on this table. I don't really want to go through it. What I really want to talk about is the fact that these are the material properties and the calculated capacities of the 5 different shapes that we used. The fiber volume ratios for the 3.2 millimeter sections, a little below 40% and a little below 50% for the 6.4 millimeter sections. All of the data that's in white background was actually experimentally determined. The remaining data, because the remaining data was calculated based on laminate theory, actually on the Eurocomp equations, and calibrated to the experimentally determined values. From these, then, we can calculate both the squash loads of the individual sections and the critical buckling loads based on the plates making up these sections. From this, we determine our plate slenderness and our classification of these sections along the very bottom here. And so we see that we've got one section that's classified as compact, one that's slender, and 3 that are in the middle, that intermediate case. And that's the one that's really most interesting to us to begin with. We started out looking at stub tests, very short column tests. We need to understand local buckling as separate from global buckling or Euler buckling. So we test some very short specimens, interested in what the post-buckling behavior is, and this is also a manner by which we can estimate the wall imperfections, which we're going to need to calculate our buckling coefficients. Case showing that we've got the 50 millimeter tube. The length is 250 millimeters, and Daniel was very ingenious and obviously had very, very long, slender fingers and was able to install strain gauges on both the outside of this section and on the inside of the wall in order to really capture the flexure in the walls themselves. You can see this section under compression, and if you look carefully, you can see the buckling of the 2 faces shown on the camera. The critical stresses were determined using the Southwell method, and what we found is they fell within about 5% of what theory was with very little variation, so we were very happy with these results, and we continue to use the Southwell method across the board to determine actual buckling capacities. Experimental data. Just an example of the stub test. It's very, very repeatable. Very little post-buckling behavior was observed, and the flexure-induced strains were, again, also very, very repeatable, very consistent from these strain gauges that, again, were installed to capture the flexure of the wall itself as it buckled. So each individual test we have to apply the Southwell method to. And so in the Southwell plot, or the Southwell method, we plot this equation here, and it's in the middle of the graph. A little bit complicated, but it gives us some really nice information very, very quickly. And so we have this data from a single test in this particular case, and we can get two pieces of information from this data that are very important to us. The intercept with the vertical axis, this point where that little red dot is right now, the inverse of that value, the inverse of that intercept, is the axial stiffness of the member, EA over L. Well, we know our cross-sectional area, we know our length, in which case we can calculate the actual modulus value for that particular cross-section. And if we take the square root of this slope here, we get a measure of the outer flatness, delta naught, of the individual plates, or the imperfections of that particular plate. So if I take a look at the data that's shown on this particular graph, we have a cross-sectional area and a length that we know for this particular shape. The intercept is at 1.71, and so we can back calculate a value of E of about 27,000 MPa in this particular case. From theory, this particular one would be about 24.7, and so we're reasonably comfortable with that value. And really what's more important is trying to estimate our plate imperfections. Square root of this slope gives us a plate imperfection of about 3/100ths of a millimeter, which corresponds to about 1.5% in terms of the plate outer flatness. And so that's a good measure for this particular product. And of course, this is going to differ depending on the protrusions that you're looking at and depending on the manufacturer as well, potentially. And so these would be values that would be given by the manufacturer for their particular material, essentially a tolerance. We then went on and did a large series of column tests where now we're looking at global buckling and the interaction between global and local buckling, and also as a means of estimating column imperfections. There were a total of 74 columns tested. Of the 5 sections we've discussed, the effective length varied from under 200 millimeters to over 2 meters, and the slenderness varied significantly from about 0.41 to 2.3. Displacements were measured along the height of the column using draw wire transducers, so we were very confident in our displacement measurements. We actually used digital image correlation in some cases as well. And the critical stresses and imperfections were all determined using the Southwell method. We are using square columns, square protruded shapes. The boundary condition that we used for the column buckling, you can see here, permits buckling in only one direction. And this is really just to simplify data for us, data reduction for us, data acquisition for us. We knew which way the column was going to buckle about one axis. And we have a range of behaviors as we might expect from very, very long columns. This is our load versus mid-height deflection relationship. Very, very long columns, quite soft, very large mid-span, mid-height deflections. And as the columns get shorter, we have a stiffer behavior, shorter mid-height deflections prior to local buckling. And in fact, we don't even have the short columns plotted on this particular plot. And we do have cutoffs, the little X values. We arbitrarily stop the test at a mid-height lateral deflection of the height over 50. And this is partially for safety issues. We don't want the columns snapping out of the test frame and flying across the lab. And so what I'm going to do is I'm going to take you through a couple of slides here that really show the progression of behavior and then eventually the interaction of behavior. And so the first slide, we look at compact sections, so relatively stocky walls, and with short columns on the left and going to longer columns on the right. And the behavior is largely what we might expect. A very short column of compact section, we end up with a true crushing type behavior, shown on the bottom left. Essentially, we're meeting the squash load. We'll jump over to the long column. Very clear global buckling behavior, no local buckling seen per se, so we've got really an Euler column here, behaving as we might expect. When we get into this intermediate range in the middle, we can certainly see a global Euler-type buckling behavior, which results then typically in crushing of the compression walls of the section, as we show in the bottom middle image. As we move to intermediate sections, we start to see a progression. So again, this is an intermediate walled section, short columns on the left, long columns on the right. In the long columns, still an Euler behavior, nothing particularly surprising there. In the short columns, every time we see these little yellow arrows, we're trying to point out local buckles starting to occur. Really, it's hard to see in this image, but if we take a look at the final failure, we can see that there was certainly some local bending stresses in this face that resulted in tearing the compression face away from the web as an ultimate failure mode. And intermediate columns actually exhibited some of that behavior, sort of a combination of this global behavior and the local behavior we saw with the short column. As we go to long, slender sections, slender cross sections, we now see very clearly the local buckling starting to take over. I think they're fairly clear in this image on the left and the image in the middle with an intermediate column, which is also exhibiting some global behavior as well, but the buckles are very pronounced. As we go to long columns, again, local buckling doesn't really affect the behavior, and we've got an Euler column. And so if we take all of our data and we group it into families, we map it on this same kind of plot that we showed before, where we have the column slenderness going from very short columns to long columns across the bottom, and the plate slenderness vertically from compact plates to slender plates. We end up with groupings of behavior. And so very short columns, very short columns, intermediate slender plates, we really don't see any global buckling behavior. It's governed by local buckling behavior. Similarly, for long columns, we're really governed by Euler behavior. Global buckling, not much interaction with local buckling over a range of slenderness values from compact and into the slender range. Really, it's this region here in red that we're most interested in. The failure modes are all involve an interaction of global and local buckling. And so that's the region of concern. Again, we can plot the same data based on its normalized capacity. And so, of course, we have the experimental data as the individual data points versus column slenderness, where we have the long columns, where essentially Euler buckling controls the behavior. In the short columns, we see a significant reduction from the perfect column down in here. And really for short columns, the imperfections have a very significant effect on the capacity. And so a lot of this behavior is a function of the individual imperfections. And then in this intermediate range, we really do get an interaction between the local buckling and the Euler buckling, and a significant reduction in behavior from the perfect column. And if we go back to that original nice mechanics approach that we proposed earlier on in the presentation, that's the red curve, which again is solely from fundamental mechanics, and it seems to capture the behavior very, very well. It captures the lower bound of the behavior very well. So we're very pleased with this result, and it gives us a basis now for building design curves. There we go, just summarizing that. There's our equation again, and that's that red curve, which certainly appears to validate the approach from fundamental mechanics, as we might expect. We have done a significant additional study. I'm not really going to go deeply into it here, involving I-shaped sections in protruded shapes, at least that are available in North America. I-shaped sections are all essentially square, so the flange width is equal to the depth of the section, and so we have 100 millimeter and 75 millimeter sections. Excuse me, we actually looked at two materials, and the attempt here was to come up with materials that had different ratios of longitudinal to shear modulus. Frankly, we were not that successful. We need to find some other formulations where we get a larger range in behavior. But we do see a little bit of a difference between the Young's modulus and the longitudinal and transverse directions in the ratio of those. And so we were trying to get some different material behaviors, and we were only marginally successful there. What we did to affect slenderness then was we cut off the ends of the flanges. And so we have in this image on the left, we have the shape as it appears, or as it's provided to us, with the flange dimension essentially the same as the depth of the section. So B over D equal to 1. And then we subsequently cut off the flange tips to get stockier, more compact flanges to a very, very small eye shape here with very, very short flanges. And the ratio varied down to about 0.44, which affected different slenderness ratios for the flanges themselves. We also tested a number more tubes in order to fill in some of the gaps. So what I want to do now is to flip gears a little bit and look at how can we apply this information and how can we apply this data to developing standards for FRP sections. And I want to come back to this last point down here, and particularly this local buckling issue. Euler buckling is not particularly a problem. We all understand it. We can calculate it. Local buckling, when we're talking about orthotropic material properties, becomes a little bit complicated. And so I want to talk a little bit about how the codes address these and how we're proposing to refine this. So if we look at current standard approaches to local buckling behavior, and I'm going to take the eye section as an example, what we do is we assume that the eye section is made up of 5 plates. So we have 4 flange outstands and a web, and that those plates are supported either on 2 edges in case of the web, or 1 edge, and they're free on the outside edge in the case of the flange outstands, and the supports are all simply supported. So essentially we're placing a hinge at this location at the intersection of the flange and the web, and calculating the buckling capacity, the resulting buckling capacity of the plates. And this is a fairly straightforward set of calculations. We have some constants that are going to be a function of the material and the geometry. So these are the D constants that appear in our buckling equation. And we can calculate this. And this is a fairly straightforward approach. It's relatively simplistic, but very easily adapted into a code environment. We'll go to the other extreme, and we can actually do a full buckling analysis. And this is an example. The analysis was presented by Collar now about 13 years ago. And we don't need to consider the interface of the flange and the web as a pin. We can actually recognize that it has inherent stiffness based on the geometry, and we can calculate the actual buckling capacity based on that geometry, based on that stiffness. And so we have our buckling coefficients. We enter into a table to consider what our edge conditions are. If we have a finite stiffness at the edge of the plate under buckling, we can still solve for capacity, and we have a whole bunch of material constants that we're going to have to calculate. This is perfectly accurate, but very, very cumbersome if we're trying to put it into a code or a standard type environment, and so not particularly practical in that sense. And so our approach that we're looking at is that we're saying that the assumption of simple supports is simply unnecessarily conservative, and as we'll see, that it estimates a capacity that's about half of what we see when we start testing these materials. And so that doesn't sound like a particularly efficient use of material if we're using that value for design, and it doesn't reflect the mechanics or the kinematics of local buckling. The rigorous approach proposed by Collar is certainly very accurate, but is remarkably cumbersome and not really appropriate for a codes or standards approach. And so what we have proposed is taking a middle ground, recognizing some simplifications that can be made, and coming up with some closed form approximations then for the plate buckling that address the real connectivity between the flange and the web without the full rigorous analysis. It would become cumbersome in a code environment. And so the first thing that we do is we take advantage of the section geometry that's available. We do not have to address all possible section geometries. We have to address the section geometries that are regularly available, that are regularly protruded. And that limits our range of applicability that we need to deal with. And that really actually helps us significantly in coming up with these approximations. We used approximate deflected shapes respecting the boundary conditions as they truly are, and continuity between the plate elements. And so if we take a look at an I section, the flange, if it's tipping to the left, or the one flange tip goes down, the other flange tip has to go up. So we have to reflect that continuity. Using energy methods, obtained approximate expressions then for the critical stress in a form that's familiar to most people dealing with buckling stresses. And so we have our plate geometry and then a factor associated with the conditions in situ. And K critical then is a function only of the section geometry and the materials. We used commonly used deformed shapes in order to make these approximations, and we did so for angles, channels, I shapes, and box sections, and consistent deformations as well. As we can see here with the I shape is a consistent set of deformations where the flanges have to tip. The web has to therefore buckle in this manner, and this flange would tip in this direction. And we considered both the isotropic material case. This is useful because we can compare our results. They should converge to the results for an isotropic material such as steel, where we have lots and lots of data and we know how the behaviors, or what behavior to expect. And we looked at 3 cases of orthotropic materials that we hope capture well the range that is likely within the protruded FRP world. And we compared these with the simply supported edge condition assumption that we presently use in the code, and also with detailed finite strip method analyses, which is very common, for instance, in the cold form steel industry. And we come up then with and this is a plot for I shapes where we have a flange to web dimension and our buckling coefficient. And we can see the 3 different orthotropic materials up to isotropic, which would be the value for steel. The posed equations that I'll show in a moment match very, very well with the so-called exact solution obtained from a finite strip method. And if we come down, we've only plotted the one value, but if we come down to the material that we called orthotropic 3, our predictions versus then the simply supported solution predictions, which are significantly different and vary by a factor of about 2, up here where BF over BW is 1, which is how we're normally, how these sections are delivered to us. Certainly there's some error as we move out of rational ranges of behavior, and so what we wanted to do is we limited these to typical shapes and their equation, fitting the equations within typically available geometries. And we see as we go out from that geometry, we do see some errors starting to occur. The nice thing is, of course, this is fundamental mechanics, and therefore if we it should converge to well-known solutions. And so if we get well-known solution for an isotropic plate material, K critical should be 4, and sure enough, our equations converge to 4, as they should. And so that's a kind of check that we're in the right ballpark. And these are the resulting equations. Now, they're certainly still complicated, a little bit more so potentially than the simply supported case, but certainly less so than the rigorous case proposed by Collar. And so we have our equations for critical buckling coefficient for angles, I shapes, channels, and boxes. And importantly then, the range of applicability, that we have to have a flange to web ratio within this range. Now this range will capture pretty much most protruded shapes that are available, certainly in North American practice. And we compared then our predictions to those of the current code over here on the far right, and we see that our predictions versus current code, we have a very significant relative difference based on these simply supported edge conditions, up to greater than 50% when we're talking about channels, and somewhere around 50% when we're talking about eye shapes. If we compare our predictions to the finite strip method within this range of applicability, we see excellent agreement, 1%, 6%. A little bit worse for channels, 10%, because of course channels, we have the shear center outside of the cross-section, which raises some complications in the analysis, and 3% for boxes. So very good behavior, in our opinion. And so what we wanted to do was take a look at this based on our data and based on experimental data available in the literature. And so we have plotted here some data available in literature from the 90s, Tomlin Barbaro's data, some data from Turvey and Zhang about 10 years ago, and then a range of our own data from wide flange shapes, from eye shapes. This group of eye shapes were as delivered, so the flange is equal to the depth, the flange width is equal to the depth of the member, and then these are ones with cut down flanges, and so the flanges are becoming stock here. And what we see is the open data are simply the behavior, the ratio of the predicted value to the experimentally determined value based on these simply supported conditions, what would be currently in the code, and we see that the ratio is down around 0.5, and in fact up here at 0.53 is our average. And then our recommended approach with the equations I showed on the previous slide are the solid data points, and we see much better agreement between the prediction and the experimental, but still on the conservative side, which is what we would like to see for a design equation. We also tighten up the variation a little bit as well. One thing that's very significant with the proposed equations, it's independent of this BF over D ratio, where we see actually worse agreement with assuming the simply supported condition as we start changing going to a wide flange. So the implications of this, we can have a code equation with these values and this nice simple approach, and then we calibrate that code equation. We calibrate the material resistance factors accordingly based on experimental data. And that's where the problem, that's where we feel the problem comes, and we end up in a slightly misleading behavior. And I'll discuss that here. So if we consider the simply supported junctions between the web and the flange, what we see is that we get a significant underestimation of the buckling capacity by a factor of approximately 2. And so a very poor representation of what's really going on, albeit the equations are relatively simple. In addition, this degree of underestimation increases as the flange slenderness increases. And so we get into these practical sections having very slender flanges as they're often delivered or as they're fabricated, we get an even greater underestimation. So we take these two facts together, we have an implication on the calibration in terms of building code material resistance factors, the so-called phi factors. If we use these current simply supported case, we end up with a phi factor that's relatively high, 0.85, 0.9, in order to make up for this underestimation of capacity. And this is misleading because it's not telling the true story. A very high phi factor misrepresents the material reliability, misrepresents the variation and the imperfections in the material, and really is only shown to be appropriate probably for wide flange shapes, which implies then that we need to have a different phi factor for different shapes, which is not a particularly practical approach from a code perspective. So if we use the same phi factor, we end up with non-uniform reliability. If we use the calibrations based on closed-form equations, we have a similar reliability across the board. We will end up with lower phi factors, lower material resistance factors, but that should be expected for this material. We feel that these are more representative and more uniformly applicable across different shapes, as we've shown, angles, channels, eye shapes, and boxes for the moment. All the equations are based on mechanical principles. There's not an empirical value, not an experimental value placed in them. They do require calibration for an individual section, and so manufacturers are going to have to essentially tell us what their K-critical values are, and this is consistent with other code provisions that we've seen in the FRP world. For instance, bond characteristics in glass fiber bars, for instance, our manufacturers need to give us that characteristic value. We've also proposed an approach which we believe improves on current practice and can be easily extended to other shapes, other material properties analytically. And so with that, I wish to conclude. We certainly have time for questions, and I'll leave this slide up, giving some of the references that are readily available in the literature to this work, and of course thanking our FRP supplier, our pultruder, local pultruder, Bedford Plastics. All the work was done in our lab here at the University of Pittsburgh, the Watkins Haggard Structural Engineering Lab, and also support of CAPAS in terms of Daniel's PhD work here. And so with that, I will conclude and open the floor or the chat room for questions. Thank you all for coming.
Thank you very much, Ken, for this very nice talk, very interesting on a very original topic. I'm not sure that we have seen in conference many of papers on this topic. Well, if any of you have any question for Kent, so you can ask them. Okay, there's one coming. Would the equations you propose, would it be maybe used for carbon FRP? Just maybe wondering if we move just for the mechanical properties, if can they be useful? If there's maybe the question is there any difference between carbon and glass?
In terms of mechanical behavior and buckling behavior, we have not experimentally looked at carbon because nobody's really pultruding carbon shapes particularly. I suspect they'd be very expensive, but there's no reason. This is based on fundamental mechanics. From a buckling perspective, I see no reason why a CFRP plate would behave any differently than a GFRP plate. And so it could certainly be extended. My opinion is that yes, it could definitely be extended to carbon, to aramid, to any other FRP. And to give an example, some people may be aware, I do a lot of work with bamboo. And bamboo is essentially an FRP material as well. It's not a polymer, but it's a fiber reinforced material with a high degree of isotropy. And we can use the same approach with bamboo. So really, this is a mechanics approach. Provided we can get the appropriate material properties, there should be no problem extending it to other orthotropic materials.
Yeah, very interesting. Is there any comment or questions?
I would add that, taking from what Emmanuel just said, this is a relatively new area. There's a lot of work going on internationally. I can only guess that I have a number of graduate students watching this right now. I'm not certain. Well, John Myers isn't. But this is an area to look into. It's a very open area for study. This study is presently being extended to look at lateral torsional buckling of beams, which adds another dimension of complexity to the problem. But this is a great area for study in the future. And so I would encourage the graduate students, the doctoral students involved, to take a look at this as an area to build your careers in.
Okay, so it seems that there is no additional comments. So next presentation will be given in beginning of May. We continue the webinar series until end of June for this year. So any comments or questions? You can ask them directly by talk, and I will open your microphone. If not, I will just like to thank Kent again. This webinar will be available online with a replay. The link will be sent with the newsletter or on the website, or I can send you directly if you send me an email. It will be available about 1 or 2 hours. It takes a little bit time to record all of this. And feel free to send the link to any of your colleagues who are working in this field, because all of this is just for free and is for trying to promote the use of FRP and the knowledge in this field. So, Kent, have a nice weekend. Thanks again for this nice presentation.
All right, thank you, and I thank everybody for attending.
Thanks. Bye.
Bye-bye.